Okay, so now that we talked about everything that's wrong with Java Futures, let's talk about how CompletableFutures fixes these problems. And we'll do this by explaining a bit about what the CompletableFutures framework is in the first place to give you the big picture view. And then I'll explain to you how the framework overcomes the problems with classic Java Futures, which are the features that have been around since 2004 or so. About a decade later, CompletableFutures were added to Java. So Java 8 came out about 2014. Futures had come into Java about 2004. And so in that intervening time, people realized they were pretty broken and set about trying to fix them in some way. So what is the CompletableFuture framework? Well, it's essentially a means of providing much more scalable and much more sensible asynchronous concurrent programming model based on reactive programming principles, as we saw in the introduction to this whole thing. At a high level, what this framework does is it supports dependent actions that are triggered or that will run when other earlier asynchronous operations complete. So that's the definition. Now, whether you could make heads or tails of anything by that definition or not is an open question. But let me give you more explanation to try to make this more clear. And to do this, I'll model some examples of dependent actions that trigger upon the completion of asynchronous operations using a data flow diagram. And so this data flow diagram, is a very simple data flow diagram, is for a web crawler. And this web crawler is something we'll talk about, and then your fourth assignment will have you implement this web crawler in all of its full-blown glory. So the way this is going to work is we will have some asynchronous task, task 1, and that's going to go ahead and start to download a web page asynchronously. So it's going to download a web page, and that web page will be downloaded in the background. And what we'll get back, as we'll see, will be a future. And then there's 2 dependent actions that are triggered after the web page is downloaded. So after the web page has been downloaded, we're going to count the number of images on the page asynchronously, and we're going to count the number of hyperlinked pages that are accessible from the page asynchronously. Both of these things will be running asynchronously. So these are also 2 asynchronous tasks. And then there's a fourth task, which will be to combine the results returned from these other 2 tasks when these 2 tasks, task 2 and task 3, finish running. So task 2 and task 3 will trigger after the completion of task 1, and task 4 will trigger after the completion of task 2 and task 3. Okay, any questions about that before I go on and show you anything more? That's a data flow diagram, shows the flow of control, and shows which tasks depend on which other tasks, and it also gives you a hint about when these tasks can run. They can only run after things that came before them have been triggered. Yeah? So is that a question about asynchronous computation, or is that just a question about, so the question was, to repeat the question, when you have any kind of limited network, any kind of limited resource, be it the number of cores, the amount of memory, the speed of your disk controller, the speed of your network, there'll be limitations, and at some point, if you do enough of something else, you'll run out of something that's limited, right? So for example, we might all drive around in Maseratis, or Ferraris that are really fast cars, but when we get out on Interstate I-65 at rush hour and you've got hundreds and thousands of cars all jammed onto one small road, everything gets backed up. So I think your question is a more general question. What happens when your cores are capable of doing more requests and downloading more stuff than the network can handle? And of course, that's just a generic problem, right? Whenever you have a situation where you can't fit everything through the soda straw thin pipe, it'll block. The cool thing about CompletableFutures is any blocking that might happen is done in a thread pool, typically a fork join pool, although you can define what pool is used, and you can even make your own pools if you want, but it'll typically be the fork join pool by default. All the blocking that might happen is done in that pool. And all the stuff we talked about before, remember we talked about fork join pools, and we talked about how you can have the managed blockers, where you can designate if someone is going to block, you can use a managed blocker, so it'll compensate by creating another thread for the fork join pool. So you could actually create more threads. Now, if the problem is not CPU computation, but it's network bandwidth, then you're just going to wait. But the good news is your application code doesn't wait. Your CompletableFutures framework does the waiting on your behalf. So the only way you would know that this was a problem would just be that your system would get sluggish. But that's always the problem with networking, right? Whenever you have something that's too slow, you're just going to back up. Just like whenever you hit the interstate at rush hour, doesn't matter how fast your car is, you're going to wait. So this is not a CompletableFutures issue, it's just a scalability issue. And of course, just again, a little digression. The history of computing has always been about different resources being the bottleneck at any given point in time. So, at one point, say, processors were really slow. And, over time, different things changed. So processors got faster, and then memory got cheaper, so we had more of it. Networks got faster, and there's kind of an arms race to see which one will keep up. Nowadays, actually, if you think about it, network bandwidth is actually probably increasing faster than CPU speed these days, right? So networks are getting faster than CPUs are getting faster. Why is that? Because CPUs have kind of maxed out at 2-point-something gigahertz, but networks keep getting more and more and more bandwidth. On the other hand, we now have more cores. So now you've got a computer with 8 cores or 16 cores or whatever. So now you can do more work. So over time, the workloads and the bottlenecks just shift around. The cool thing about the asynchronous programming model, to bring this back to our discussion, is all these issues just sort of disappear from the programmer's point of view, and it becomes the responsibility of the frameworks to figure out how to handle these kinds of things. So let's take a look now. This is just a little bit of pseudocode that is it's a bit more programmatic than my data flow diagram, but it's representing the same thing. So this is just kind of showing some of the asynchronous calls that are available in the CompletableFutures framework and demonstrating at a high level how they work. Later, we will look at this example in full-blown glory to see how it is implemented, but it would be way too complicated to show you on one page. And that's kind of interesting because one of the things you'll discover with CompletableFutures is it's much more difficult to show a simple example of CompletableFutures. Whereas it's very easy to show a simple example of parallel streams. To do the same thing, you can just get more stuff packed together with parallel streams syntactically than CompletableFutures. And that really has to do with the inversion of control behavior and the asynchronous nature of CompletableFutures. So that's why I have this little pseudocode example. So what we're going to do up here is we're going to go ahead and get the start page, right? That's kind of like get the start page. But we're going to do it asynchronously. And there's a method called supply async where you give it a synchronous piece of code that goes out and downloads a page, but we're going to do it asynchronously. And what we get back from the supply async call, which is part of the CompletableFutures framework, is a future to the downloaded page. So initially, of course, that future will not be ready, so we'll just get back a future. And I represent that future diagrammatically as table tent number 8. So remember I said that we could then have dependent actions that trigger upon the completion of asynchronous operations. So the two things that are going to trigger on the completion of asynchronous operations are counting the images on the page asynchronously and counting the images on all hyperlink pages accessible from this page asynchronously. And that's what these two pieces of pseudocode are showing. So here, when this future 8, completes, this code will then run. And likewise, when this future completes, because it's the same future, same completable future, this code will also trigger. And so both of these computations can actually start running at the same time once this one finishes. So that's an example of forking operation. So we're forking things off. So now we have two things that are running. And this is going to go out and asynchronously count the number of images on this page. And this guy will go and asynchronously crawl all the hyperlinks reachable from this page, and it'll return a completable future to a count of those images. And this one will return a completable future to a count of the number of images on this page. So both of these things here, both of these computations, the then apply async and then compose async, will be running in parallel. And then this final computation, which corresponded to combine the results to create the total asynchronously, will wait until both image 1's future and image 2 future, right? This one, number 1, and number 26. It'll wait till both of those are finished, and then it'll combine the results by summing them together. So this is an example of joining. So we have forking, we have chaining. This is an example of chaining. And then we finally have joining, which is bringing them back together again. But it's all done asynchronously, right? So it's under the hood, of course, this is all using the fork join framework, fork join pool framework. But the programming model is completely different than the classic synchronous programming model that you would get with, say, parallel streams, which does more or less the same thing, but it does it synchronously as opposed to asynchronously. All right, so that's the high-level view. Later, we will walk through this code in more detail. And your assignment number 4 is a variant of this that does more than just count the images. It also downloads them. A couple things to note here. You can dictate what thread pool these computations run in. And by default, it uses the common fork join pool if you don't specify something to the contrary. Or you can designate the type of thread pool, which could be one of the built-in thread pools. You could use a fixed thread pool. You can use a cached thread pool. Or you can also make your own thread pool if you so desire. And as long as it conforms to the executor interface, you can pass it in and use it with the framework and use whatever you might happen to pass in. That's really cool. That's a little different from parallel streams, where parallel streams, you couldn't designate the pool. With completable futures, you can. Another thing to note here, just as a side remark, and we'll come back and look at this in much more detail later, it's really powerful to combine completable futures, sequential streams, and functional programming features like method references or lambda expressions. And here's an example that we'll talk about called the image stream gang program. You saw the parallel streams version of this week or two ago. Later, probably next week, we're going to talk about the completable futures implementation of image stream gang, which, as you will see, is way faster than the parallel streams version, and even more faster, of course, than the sequential version. And this uses a sequential stream along with method references in conjunction with completable futures. So we actually end up with a stream of completable futures here, as opposed to a stream of just regular old values. And this is really, really, really powerful. It's also somewhat complicated to understand, though once you understand streams and you understand completable futures and how they work together, you'll see how it's really, really cool way to do things that's not that much harder to program, but will perform much more efficiently. So it's just a cool example of how the combination of all these features are really powerful. And this is actually also an example, this is an example more of sort of reactive streams or reactive programming. So we've got a stream that's reactive with asynchronous operations, and we've got streams of values, mostly completable futures, being passed through that stream. Another cool thing about the completable futures framework, much like parallel streams, as we talked about before, is that you can write very scalable, very powerful parallel programs or concurrent apps that need no explicit synchronization and don't have any explicit threading, which eliminates a lot of the inherent and accidental complexities of building concurrent and parallel programs. So as you'll see, and I'll walk you through some examples later, you can use some threads if you need them, but nobody would do that. You'd use other mechanisms like supply async, which doesn't explicitly expose the threading API at all. In such cases, in cases where you don't need any synchronization, it's typically because you're using Java class libraries to implement the stuff, and they build the necessary synchronization into the library. Oftentimes, you don't need synchronization at all. When you do need it, you can easily get it by using something like a concurrent hash map or something else that has concurrency built into it very efficiently. All right, now that we've talked a little bit about completable futures, and I've given you just a taste of what they do, let's briefly go through how they overcome limitations with the Java futures stuff we talked about before. So one thing you can do with a completable future is, as the name suggests, you can complete it. So here's a simple example. We'll look at this example in more detail later, but we create ourselves a completable future that actually has no computation associated with it whatsoever. We just have a future that's just uncompleted. Then we go ahead and spawn a thread, and this thread is going to do something. Let's say it's going to multiply big fractions or whatever, right? And after that thread starts, then it'll be running in the background, and at some point, there could be other things running in the foreground, so these things are going in parallel. And when we get to a point where we know that we're finished with whatever computation was running here, we need to be able to complete it. So all you have to do is just say future.complete, and you would pass in whatever the return value was from this computation. For example, if you're multiplying big fractions, it might be the result. So you say to the future, you are now done. That will update the future's result, and anybody who would be waiting for the future to complete can now return and finish. And so we'll talk later about what complete does. We'll talk later about what join does. But this is essentially a runtime exception-based version of the get method we saw before that doesn't do checked exception handling. So you can use it a little cleaner. So that's one example. You can complete futures that are already running. Another thing you can do with futures, completable futures, which you cannot do with vanilla futures, is you can chain them together in a fluent manner. So I mentioned this before, and I said you probably, if you don't know what fluent programming is, it wouldn't make any sense. I think when you see the example, it'll make more sense because you've probably used this before in other programming languages. For more information about fluent programming, take a look at the link here at the bottom of the page. So here's an example of fluent programming applied to completable futures. So we say completable future.supply async. Supply async is a factory method that takes whatever lambda or method reference is passed to it and arranges to run it in the background. So this is now going to be running in the background. And what it returns, what supply async returns, is a completable future to whatever type this thing is. So in this case, it's going to come back as a big fraction. So supply async will return a completable future. This will then go off and run in the background. When the computation being done by this lambda expression or this functional object completes, the future returned from supply async completes. And then we do the next dependent action, which in this case is what's called then apply. We'll talk more about what then apply does later. What then apply does is it goes ahead and takes the result of this asynchronous operation, and it goes ahead and takes the reduced fraction and turns it into a mixed fraction. For those of you who haven't done fractions in a long time, you can have what are called improper fractions, which would be something like, 18/4. And if you create that into a mixed or a proper fraction, that'll turn it to what, 4 2/4, or something like that, right? It'll give you back in a mixed string. This then apply method also returns a completable future. And when this operation is done, that future becomes triggered or completed. And that triggers this next method in the chain of Fluent method calls to run. And that will, in this case, go ahead and print the results out. So this will get a big fraction as the result of then apply, and then we go ahead and print it out. And the point of this is that the action at each of these completion stages is triggered when the future from the previous stage completes asynchronously. So it'll be running, it'll be done, it gets triggered, then the next thing can run. So that's what's called a fluent interface. You can have these things done one after another, and each one of them works on the results of the previous stage, and it gets triggered when the previous stage's asynchronous computation finishes. we will talk about that a lot more. That's the heart of what's going on with completable futures and why they're so cool and why there's so much of an improvement over Java 5 futures, because you can chain them together. There's some other things you can do too that are really cool. So I think, first of all, the ability to chain stuff together is pretty cool, but this next thing is even cooler. You can trigger the futures reactively and efficiently using a collection of futures without any additional overhead or complexity from your programming perspective. This, again, is something you just couldn't do at all with classic futures. So here's a really interesting example. We'll look at this example in more detail as we go through the slides. This example generates a stream of big fractions, random big fractions, up to this amount. It goes ahead and multiplies the big fractions by some constant, which is also a big fraction. And so what we have here is we have a stream of random big fractions up to this amount. We then multiply that stream of big fractions asynchronously. So now we end up with a stream of completable futures to big fractions that are all running in parallel. So we've got, let's say, for sake of argument, we have 100 big fractions. After the map call, we'll then have 100 asynchronous multiplications of random big fractions. And then what we're going to do is we're going to collect these things together using a collector that will do essentially what we'll talk about later as an arbitrary arity method, which takes an array of running futures and gives you a single completable future that you can use to wait for all those other futures to finish running. So that's why it's reactive. So we're going to get a single completable future to a list of big fractions. That's what we get. This is called, future to list, or completable future to list. So that's what this does. So at this point, after we get done with collect, we've got a completable future. There are now 100 asynchronous operations running, cranking away, doing work on 100 of these big fractions. And what we can say then is, when all of those completable futures finish, then and only then, go ahead and print the resulting list. That's what this says. Future to list, then except says, don't do anything until everything else is finished in those other 100 completable futures. So it allows us to be able to react when all the other things are finished. So it's really, really powerful, and we'll talk a lot about this. This is super cool, and I've also created a really interesting set of collector implementations that work on completable futures, and they're really powerful. So we only print the results after everything else has been finished. Notice also this example illustrates, once again, the power of combining a sequential stream with completable futures. And the analogy I always use, because sadly I'm a huge Reese's Peanut Butter Cup fan. Chocolate tastes good on its own, peanut butter tastes good on its own, but when you combine them into a Reese's Peanut Butter Cup, it's really tasty, right? So it's the combination that's even better than each of the ones separately. Oddly enough, I do run across people who don't like the combination of peanut butter and chocolate, but I just can't understand why they don't like that. It's great. Okay, so that's the end of the overview. Hopefully I've kind of motivated for you why we should care about completable futures and given you a little hint as to how they work. But at this point, you'd probably still be hard-pressed to program any kind of application other than a very simple example using the features we've talked about. So I will continue to elaborate upon that in the upcoming parts of the lesson.